Hi everyone, my name is Carolyn Chapel, and today's video is going to be about some of the terminology that is used in statistics. We are just starting this course, and the first thing we must learn how to do is talk using the same language that statisticians will use. So we're going to go through Module 1. And this is on concepts of statistics. First of all, we need to know what a statistics really is. So the definition of statistics. It is the science of collecting, describing, and interpreting data. There's basically two branches, descriptive and inferential. First of all, in this course that you're taking, we won't be doing a lot of the collecting, but we will talk about how it is done a little bit. We also will do some describing of our data, and we will do a little bit of the interpretation. Now, in the real world, statisticians will do a lot of all of these three parts. There are two branches. One is called descriptive and the other is called inferential. We're going to learn the differences and some of the similarities between the two. So I kind of have a picture here that can help us. The two branches, differential and inferential. And a descriptive, first of all, it just describes the situation. It's basically just telling us the facts. It will either do some of those descriptives in verbal form, written form, or maybe even graphical form. Sometimes they will also summarize our data. They do not do any predicting of any kind. They just take the data and just tell us what the data is. Inferential, on the other hand, may also take what descriptive has done, the words, the data itself, but then they go a little bit further and they start to estimate maybe what these things tell us about the entire population. So they kind of infer some sort of information onto our population. So, yeah, that's kind of what I just said. Descriptive statistics refer to the analysis of data. So again, analysis of data, might have taken the data, created a picture of some sort, circle graphs of any kind. They may have actually calculated numerical information, but they just basically describe it. They give it to us, they show it, they summarize it in lots of different ways. They can find means, median ranges. The inferentials go a little bit further, like I said, and they take those pieces and they infer something about the entire population. Okay. Um, kind of just walking through the notes that I have written for you. So the easiest way to distinguish is kind of look at what they are giving you. So I think I might have a couple examples coming down here. So basically we want to, if we can distinguish, is kind of identify the purpose. What are they trying to do in this situation? And then trying to see, is this a descriptive? Are they just telling us the story, or are they trying to imply something further from that story? So going beyond just the statements. So here are some examples. So a recent report from a police chief in New York City stated that the number of robberies in 2015 was up by 392 cases from the previous year. Okay. This is an example of a descriptive situation because they are just telling us that the number of cases was up. They didn't go and try to explain why or anything of that nature. They just told us, they went and counted how many there were, and they just summarized their findings. Okay, number two. This one's a little bit longer to read. So suppose a hot dog manufacturer claims that one of its brands of hot dogs has a mean fat content of 18 grams per hot dog. Consumers of this brand would probably not be disturbed if the mean was less than 18, but would be unhappy if it exceeds 18 grams of fat. An independent testing organization is asked to analyze a random sample of 36 hot dogs. The fat content for each of the 36 hot dogs is measured, and the sample mean is calculated to be 18.4 grams with a sample standard deviation of 1.5 grams. First of all, don't be concerned that you're not quite understanding the idea of mean and standard deviation. That is not important right now at this stage, being able to determine if it is descriptive or inferential. We can do that without really knowing what those numbers mean. We'll figure those things out as you go further into your statistical courses. The analysis results in the conclusion that the mean fat content for this brand of hot dogs from the manufacturer does not seem to exceed 18 grams. So this is an example of an inferential because they took that information, that 18.4 and that 1.5, and they did some stuff to it. And then they decided that, oh, okay, the manufacturers aren't really more than that 18 grams. Now, to me, 18.4 is larger than 18, but whatever statistical methods they use, they determined that for whatever reason, it really isn't big enough from that 18 to say that all these hot dogs have more than 18 grams. So that is one way that we infer a sample onto the entire group of hot dogs. Okay. Number 3 here says of the 93 pounds of milk produced in the United States in 2014, sorry for some of the dated information. I did just take these from other sources. So they are going to be a little dated. 4.2% of the total was produced in the state of Michigan. Okay. This one is also just a descriptive because, again, it is just stating the information. It's not trying to take that information further. Number 4, based on data obtained in a survey, it is estimated that men are employed in science, technology, engineering, and mathematics. That's referred to as our STEM areas, occupations at twice the rate of women, 31 for men compared to 15% for women. Again, they did some estimating. So estimating means they are doing a inferential type of situation because they are, again, taking their little sample and estimating it to all men and women, not just telling us that 31% of their sample and 15% of their sample were men and women. They then estimated it to say that about all men and women. So the biggest difference is to kind of look and see, did they take that basic information, whatever that information was in the study, and go further with it? Inferential statistics goes further than that descriptive. Okay. Some other terminology that I'm going to talk about in this video is being able to determine what is the population and what is the sample that we're talking about. The population is everything that we are concerned about. Now, that could be people, it could be cans of soup in a factory. It could be the temperature outside. It could be the time it takes you to tie your shoe. It could be anything that we are interested in. So the population is every piece. So when I'm tying my shoe, I'd be talking about every time I tie my shoe. So how long does it take me to tie my shoe? A sample is going to be a smaller set or a smaller grouping of those subjects. So in my tying of the shoe example, maybe I measure how fast it took me on Mondays, or maybe I pick a few days of the week, Monday, Wednesday, Friday, or maybe I do it every January 3rd and December 18th and pick a couple days of the year for however many days of the year I wanted to study this and see if I've gotten faster or slower or something. But the sample would be that little subgroup that I'm actually going to collect data on. Okay. Being able to tell what the population is and what is our sample is kind of an important thing as we progress through statistics, because we want to make sure we can clearly identify who are we talking about as our population, or what are we talking about, and then being able to decide which is our smaller group that we're looking at more closely to get the information from. So I have a couple examples here. The registrar at the University of Michigan is interested in determining whether students were satisfied with the registration process. 200 students are surveyed and asked to respond to the following question. How satisfied were you with the process of registration for this class this fall? Okay, so the population, remembering population is the bigger picture, like everybody. So when we're talking about registration, we are talking about all of the students. And in this case, it'd just be the ones at Michigan, University of Michigan. We are not concerned about the students at some other college because right now we're just concentrating on the students at the University of Michigan. So that is our population. The sample is the actual 200 students that they surveyed, who they actually went and asked the question to. Number two, we have a company who took a sample of 200 bottles from the production line to see if the measurements were up to standards. So the population would have been all the bottles in their production line. Okay, because we're looking at all the bottles that are measurements that they're concerned about, but the 200 that they actually looked at to take the measurements from, that would be our sample. Okay. Hopefully these examples are helping you understand the difference between the population and the sample. I could talk about a population of all my stats students, and then a sample could be the ones that are just this semester. Okay. Now, when we have data falls into a number of categories, and we want to be able to understand the data. And to understand data is the measurements we're taking or the pieces of information that we're taking. They're gonna fall into categories, and how we study them will be different based on the type of data that we have. So first of all, a variable is a characteristic that may change from one thing to another. So your height, your weight, your hair color, your zip code, your number of siblings you have, the number of credits you're taking at a college, the time it takes you to tie your shoe. All of those things are considered variables. And every person has lots of variables that are associated with us. Data is the value to those variables. So my hair color is brown. My eyes are brown. I'm 5'5". I'm not going to disclose my weight. I haven't timed how long it takes me to tie a shoe, but I'd say anywhere between 30 seconds, and I have really no idea how long it takes me to tie a shoe. My zip code is a 5-digit number that I, again, am not going to disclose, but those are the data that are associated with me, and everybody has other different types of data. Data does fall into two types of category. It can be either qualitative or it can be quantitative. Now, there is a little bit of, we have to be a little bit careful. Just because something is a number does not automatically make it numerical. Okay, so when we talk about categorical or qualitative, it's just kind of a way to group us together, if you want to think of it that way. So all the brown-haired people would be in one group, all the red-headed people would be in another group. Numerical is a little bit different because we can actually take those numerical values and order them in an order that makes sense. Now, being like when one number is bigger than other, it actually means that I have more of that thing. Like my height is 5'5" and somebody else is 5'4". I am taller than that person. If I weighed 105 pounds and someone weighed 83 pounds, I am heavier than them. So numerical is actually has a quantity, how much of something we have. So, and a lot of times can we say, when we think of numerical measures, can we do numerical processes on them? So can we add them, subtract them, multiply and divide? And that answer still makes sense somewhat. Okay, so we're going to kind of decide on these if it is a categorical or qualitative or numerical, and that's sometimes referred to as quantitative variables. So the types of music that there's out there, so your rap and your pop and your jazz and your classical and all those other types of music. I'm not going to list them all. Those are going to be considered categorical data because it's a category. The number of credits a student is taking, first of all, it is a number. And it is numerical because we can order that and it makes sense. So I'm taking 17 credits, you're taking 15 credits. I am taking more than you. The difference between the two, we could subtract them. We could add them if we wanted to. Doesn't make a whole lot of sense to multiply or divide, but it does make sense. We could add and subtract. So those would be numerical or quantitative. Our height and weight both do fall into the same category. They are both numerical. And because we could add and subtract values if we wanted to. Our zip code is a number. However, this is one that we have a number that is actually categorical. So it kind of just groups us into an area. Does not, I mean, we aren't going to take somebody's zip code and say, I have more zip code than you do. That just doesn't make sense. So zip code is a categorical piece of data. Even though it's numerical, it is still, even though it's a number, it's not numerical as far as when we talk about categorizing data. It is a categorical or qualitative piece of data. Our cause of death, that is not a number, so that will be our categorical. Age of death is going to be numerical because we do talk about me being older than you or younger than you, and we can subtract ages. A hospital ID number, again, is a form, or any ID number, to be honest. If it's a number, it is still categorical. It does not have any meaning to like a quality or quantity of something. I mean, I have more ID than you do. It does not make sense. So one thing you can be assured of is if it is not a number for some reason, it will be a categorical situation. However, numbers, we have to be a little bit more careful because some numbers are categorical. So the number has to represent a quantity, how much of something. Yeah, we don't have how much ID number you have. Okay. When we do have numerical data, we can actually go a little bit further and break them into two different categories. We can talk about something being discrete or something being continuous. I like to think of this on a number line. So if you're thinking of a number line, we've all seen these back in grade school. And if we talk about a discrete variable, now we're not talking about the actual value of a specific person's data. We're talking about all possible outcomes for these variables. when we look at all the outcomes that we could have, a discrete is going to be a bunch of dots on our number line. So there'll be like 1 and 2 and 3 and 4. We could even have fractions like 1, 1.5, 2, 2.5, but they're just dots on that number line, isolated points on the number line. A continuous variable has outcomes that could be from something to another value. So a continuous interval, so to speak, like the number of water in the amount of water in a jar, because it basically think of yourself as you're filling that jar, you're starting with nothing and it's going to continuously fill up or continually fill up. The time is starts and then it ends, continuous piece. Number of siblings you have 1 and 2, 3. The number of classes you're taking, you have 1 class, 2 classes. You don't have one and then and a continual filling up the, yeah, you don't have like 1 and a little bit of a class. Okay, some examples here as that as well to give us a little bit more understanding between discrete number of points, just discrete values separated on our number line, or a continual type thing. The yield in bushels of field corn. Now this one could be a little bit tricky. If you just talked about the yield, think about when they do gather field corn and the corn is being picked. This one would be a continuous type situation because we could talk about bushels as 1.000005 and then just a smidge bigger. So technically this one would be a continuous spectrum. Think of picking up our corn and filling up the bucket. It's going to have to be continually filled. Same with the amount in a syringe. You're going to pull that medicine into the syringe. It's going to continuously fill from like empty at 0 up to however the biggest you can put in there. The cost of gasoline, that one is discrete because our cost is measured in cents. So we can have $1.15. We could have $1.16. We don't have $1.15 and micro pennies. Shoe size, discrete, because we order shoes a size 7, size 8. We could even have half sizes, but we don't have that continuous spectrum of being able to buy shoes. Our foot size, on the other hand, is a continuous thing because our foot measures from, I don't know what the smallest foot is, 15, I don't know, really, really tiny baby feet, which may be an inch or something in length, all the way up until I'm just going to be 36 inches, which is a yard, which I know no one has that big of feet unless you're wearing clown extensions or something. But foot size would be a continuous situation. Our shoes are discrete. Our feet are not because our feet don't always fit perfectly in those shoes. Temperature is a continuous measurement because if you think of the mercury going up or down on the scale, it goes continually up and comes continually down. It doesn't stop and just jump from 1 degree to 2 degrees to 3 degrees. It has to go smoothly from one to the other. There is one variable here that I didn't have on the list that is sometimes viewed both ways, and that is age, because we can look at our age by how many years you've been alive, because you can say your age is 17, 23, 36, 5, or you can think of the age as the time you've been alive, as far as like years, months, days, hours, minutes, seconds, and so on down the line. So you could think anything time related can be thought of in a continual spectrum, but sometimes we look at age in a discrete format as well. So just be aware that there are some variables out there that do kind of work both ways. And that bushel one might have been one as well. If we allowed ourselves to think yield would be definitely continuous, but if we were just allowing us to just look at whole bushels, 1 bushels, 2 bushel, then we'd be at a discrete type thing. Okay. Couple more terminologies here for this first unit, first section. We are going to be talking about numbers or measurements, and a parameter, first of all, that's going to be a number that describes the entire population. So if we went out and collected a piece of data from all the population, and then we did something with that data, and I'm going to use one that's going to come up like the average. If we did something like that on our entire population, that would be considered a parameter. A statistic is that same type of thing, but only doing it on a sample. So one way to kind of help you remember is that statistics come from samples. Parameters come from populations. Both of these start with S. Both of these guys start with the letter P. We will use different symbols to help us determine which is which. A lot of times we will use Greek symbols to designate parameters, and we'll use the regular letters for statistics. And we'll see those as you get into some of the specific statistics and parameters. So let's just do a couple examples here. So a consumer product industry shows that 97% of all US households use toilet paper. You think the percentage is crazy and survey 100 of your closest friends. You find 99% of your friends use toilet paper. So the 97% that's in there, first of all, it's done on all US households. And if that was our population, just the ones in the US, that would be a parameter. If we were talking worldwide, that would still be a statistic, because then the US would just be a sample of the whole world. But in this problem, it was supposed to be meant as a population. So that would be our parameter. The 99% that's there in that piece is actually a statistic because it comes from the sample that we took of our friends, those 100 friends. So our population here is the US households. The sample is our friends. The statistic is the 99. The parameter on the population is that 97. Okay. The average height of young women, 18 to 24, is 64.5 inches. Random sample of 50 women, of that same age gave us that average height of 24.25. So in these problems, it's kind of helpful to, again, identify the population because the parameter goes with the population, and then our sample and the statistic goes with our sample. So our population is all women ages 18 to 24 in the United States. That's our population. So the 64.5 would be that parameter. The sample was the 50 women. The 64.25 then would be a statistic. Hopefully going through these examples, it helps you get a little bit better understanding of some of the terminology we will be using. As you continue through some of my videos, you will be seeing more terminology in the first few, but then we will start using some of those pieces as we discuss further topics in statistics itself. Hopefully you are learning a lot. I look forward to continuing our videos. Have a great day.